Imagine a small factory in Michigan. The year is 1940. The storm of war gathers over Europe, and in America, an unspoken countdown has begun. Inside Hastings Manufacturing, a company known for a humble automotive part, engineers are working around the clock. Their focus isn't on weapons or warships. They are obsessed with an invisible component, a tiny circle of metal deep within an engine that no one ever thinks about until it's too late, the piston ring. And they are facing an absolute disaster. The standard cast iron rings, a design they'd used since the early 20s, were failing spectacularly. In a typical car, they might last 20,000 miles. But the military was now pushing the boundaries with colossal aircraft engines. We're talking 2,000 horsepower behemoths with 18 cylinders firing in a symphony of controlled violence, spinning at 3,000 RPM. Inside these infernos, with temperatures reaching nearly 1,200 degrees Fahrenheit, the cast iron piston rings were simply giving up after only 40 hours of operation. Just 40 hours. That translates to perhaps 4 flights over hostile territory before the entire engine had to be stripped down for a complete overhaul. This wasn't a small issue. It was a potential crippling blow to the Allied war efforts before America even officially joined the fight. To grasp the severity, you first have to appreciate the piston ring's vital role. Think of it as the engine's gatekeeper. It nestles into a small channel on the piston's side. When fuel and air ignite, the ring expands, creating a perfect seal against the cylinder wall. It captures the explosive force of combustion, channeling that raw power downward to drive the piston. Without that perfect seal, the blast escapes past the piston in a phenomenon called blow-by. The engine hemorrhages power, starts consuming oil, and essentially suffocates on its own exhaust. But forming a seal is just one of its jobs. The ring is also a janitor. As the piston cycles up and down thousands of times a minute, the engine's interior is drenched in lubricating oil. If too much oil gets into the combustion chamber, the engine will belch thick, revealing smoke. So the ring scrapes the excess oil away, returning it to the crankcase. It leaves behind a microscopic film for lubrication, just enough to prevent friction, but not enough to burn. And then there's heat management. The crown of the piston glows a sinister, dull red under load. The ring must act as a thermal conduit, transferring that intense heat away from the piston and into the liquid-cooled cylinder wall. It's a heat bridge connecting the piston to the engine's circulatory system. What happens if this bridge collapses? The piston overheats, swells, and grinds to a halt. The engine seizes, the propeller freezes, and the aircraft simply falls from the sky. So when military officials arrived at Hastings in 1940 with a demand for rings that could endure 200 hours, not a mere 40, the engineers felt they were being tasked with rewriting the rules of materials science. Cast iron simply couldn't take the punishment. The material was too fragile. Under extreme heat, it lost its essential springiness and failed to seal. The carbon within the iron would oxidize, causing the ring to literally wear itself into dust. By the 50-hour mark, it was just metal scraping against metal. By hour 80, it was useless debris. This wasn't just Hastings' problem either. Every single piston ring maker in the nation was hitting the same unyielding wall. Pratt & Whitney was developing its legendary R2800 double wasp. Wright Aeronautical was crafting the R3350 duplex Cyclone. Allison was perfecting its V1710. These were the power plants destined for the P-47 Thunderbolt, the B-29 Superfortress, and the P-38 Lightning. Yet without rings that could withstand the inferno, these incredible engines were nothing more than elaborate metal sculptures. In June of 1940, a lead engineer at Hastings named Howard Fletcher proposed a truly unconventional solution. Let's abandon cast iron, he suggested. Let's start thinking like armorers. The barrels of military rifles and cannons were lined with chrome. Chromium was exceptionally hard, it resisted incredible heat, and it didn't oxidize. This practice of chrome plating had been used in firearms since the late 1930s. If it could shield a gun barrel from the brutal, erosive force of exploding gunpowder, could it perhaps protect a piston ring from the fury of an engine's combustion? There was one major obstacle. No one had ever managed to reliably apply a chrome plate to a piston ring. The electroplating process involved immersing the component in a chemical bath and running a powerful electric current through it. Chrome ions would then meticulously bond to the metal surface. The resulting layer was only 5/10,000ths of an inch thick, slimmer than a human hair, but its hardness was off the charts, measuring 70 on the Rockwell C scale. That's harder than many industrial cutting tools. The first experimental rings emerged from their chrome bath in July 1940. They were flawless, gleaming like polished silver jewelry. But when installed in a test engine and run for just 6 hours, the results were catastrophic. The chrome fractured, it sheared off in large flakes. These razor-sharp pieces then became embedded in the softer aluminum pistons like shrapnel. The entire engine was destroyed. The culprit was thermal shock. An engine starts at ambient temperature, but quickly soars to operating temperatures where the ring reaches 400 degrees. The cast iron base material expanded under the heat, but the chrome layer on top couldn't expand at the same rate. The bond between the two different materials simply broke apart. The chrome popped off like old peeling paint. Fletcher returned to his chemical formulas. He tested dozens of different plating solutions and varied the current densities. He tried preheating the rings before plating them. He attempted to build the layer up with multiple ultra-thin coats instead of one thicker one. He introduced sulfur into the bath, then lead. Nothing was working. By October 1940, the entire project was teetering on the edge of failure. It was then that Fletcher made a desperate gamble. What if the plating itself wasn't the core issue? What if the foundation was the wrong choice? Cast iron was simply too stiff and brittle. What if they used steel as the base material instead? Steel was much more elastic and could better absorb the thermal stresses without fracturing. It was significantly stronger, capable of withstanding higher pressures. But steel presented its own unique challenge. Steel was much harder than the cast iron cylinder walls. If you placed a raw steel ring inside a cast iron cylinder, the ring would behave like a metal file, carving destructive grooves into the cylinder. The engine would be ruined in a matter of hours. This was the exact reason everyone used cast iron rings in the first place. They were designed to be the sacrificial component, wearing down themselves instead of the expensive engine block. But that was before the idea of plating them with ultra-hard chrome. Fletcher persuaded his superiors to order a batch of steel blanks. They showed up in November 1940. The new steel rings were meticulously cut, formed, heat-treated, and finally sent to the plating tanks. Once they were ready, Fletcher carefully installed them in a test engine. He started it up. It ran. 1 hour, 2 hours, 5, then 10 hours passed with the engine screaming at maximum throttle. 20 hours, 30 hours, 40. Fletcher hardly dared to be optimistic. 50 hours, 60 hours. Finally, at the 80-hour mark, he shut it down and disassembled it. The rings were immaculate. The chrome hadn't cracked or flaked. It showed no signs of wear, aside from microscopic surface scratches confirming it had been doing its job. The ring retained its original tension, the cylinder wall was untouched, with no scoring or damage. The oil was pristine, free of metal fragments. The engine had not only survived twice the military's requirement, but it was also in perfect health. Fletcher repeated the test, pushing it further. He ran it for 150 hours, then 200, then an astonishing 300 hours. The rings refused to fail. They just kept performing.
The chrome surface was so incredibly hard and smooth that friction was reduced to a bare minimum. The oil film between the ring and cylinder could be thinner than ever before. Less oil meant less resistance. Less resistance translated directly into more horsepower. The engine wasn't just more reliable, it was more powerful. But this technological triumph soon gained a darker urgency. In December 1941, the attack on Pearl Harbor plunged America into global war. Suddenly, Hastings wasn't merely solving an engineering puzzle. They were now in the business of keeping pilots alive. Every extra hour of engine life was one less hour a bomber crew had to spend dreading an engine fire over the vast Pacific. Every hour was an hour a fighter pilot could dedicate to engaging enemy aircraft over Europe instead of desperately trying to limp back to base. The military immediately placed an order for 50,000 sets of chrome-plated piston rings. That order quickly grew to 100,000 and then to 500,000. Hastings was overwhelmed. They had 3 small plating tanks. They needed 30. Then they started running out of chrome. Chrome was a strategic resource, with most of it sourced from South Africa and the Soviet Union. The shipping lanes were perilous, with German U-boats sinking Allied cargo vessels at an alarming rate. Every single pound of chromium that reached the Michigan factory was more precious than gold. The company hired metallurgists to find ways to make the plating even thinner. If they could achieve the same hardness with a more delicate layer, they could stretch their limited supply. They carefully reduced the thickness from 5/10,000ths of an inch to 3, then down to 2. The rings continued to perform. They were balancing on a knife's edge. Too thick and the nation's chrome supply would be exhausted. Too thin and the plating would wear away prematurely in combat. They had to discover the absolute minimum effective thickness. By the middle of 1942, Hastings was running 15 plating lines, 24 hours a day. Women took over many of the factory floor jobs, as most of the men had been drafted. The plating solution itself, hexavalent chromium, was dangerously toxic. It caused severe chemical burns and long-term lung damage. The workers wore rubber gloves and rudimentary gas masks, but the ventilation systems were poor. Some fell ill and had to quit, yet most of them stayed. They understood exactly what was on the line. Their own brothers, sons, and husbands were flying the very planes that relied on these rings. The production line became a masterclass in precision and velocity. Each ring began as a coil of high-grade spring steel. The steel was unspooled and sheared into strips, which were then formed into circles. These circles underwent a precise heat treatment process to give them the correct amount of tension. Too soft and the ring wouldn't form a tight seal. Too hard and it would become brittle and shatter under pressure. This heat treatment had to be perfect. A deviation of just 5 degrees could mean the difference between a ring that lasted 300 hours and one that failed in 20. After heat treatment, the rings moved to the grinding stations. They had to be ground to incredibly precise dimensions. The outer diameter needed to match the cylinder bore to within 0.002 of an inch. The ring's thickness had to be perfectly uniform around its entire circumference, as any slight variation would lead to uneven wear. The grinding wheels themselves were impregnated with diamonds and wore out after just a few hundred rings. At $50 per wheel, the factory was burning through 10 of them every single day. Next came gap cutting. Every piston ring has a small opening that allows it to be compressed for installation. The size of this gap is absolutely critical. If it's too large, hot combustion gases will escape. If it's too small, the ring will expand from heat and seize inside the cylinder. The gap had to be cut with a precision of 0.005 of an inch. Workers used specialized jigs, with each cut taking about 15 seconds. A proficient operator could process 4 rings a minute for 8 hours straight, 6 days a week. After cutting, the rings were sent for cleaning. They were submerged in a degreasing solution to strip away any residual oil or contaminants, rinsed in distilled water, and dried with compressed air. A single fingerprint, a speck of dust, or a trace of oil could ruin the chrome's bond. The workers wore clean, white cotton gloves, handling the rings as if they were precious gems. Meanwhile, halfway across the world in the Pacific Theater, the chrome rings were validating their worth under the most hellish conditions imaginable. The R-3350 engines that powered the B-29 bombers were infamous for overheating. The rear cylinders could get so hot that the magnesium crankcases would sometimes spontaneously ignite. These fires burned at 3,000 degrees, hot enough to melt through a plane's main wing spar in seconds. Entire aircraft would disintegrate in the sky, yet the chrome-plated rings held fast. Even as other components were failing, the rings maintained their seal. They kept the explosive forces contained and the engines turning just long enough for crews to shut them down and feather the props before a fire could consume the plane. There's a story, perhaps an embellishment of war, perhaps not, of a B-17 that sustained heavy flak damage over Germany. The number 2 engine was struck, cracking a cylinder head and spraying coolant everywhere. The engine should have seized instantly, but its chrome rings continued to function, sealing the chamber even with part of the cylinder gone. The pilot managed to keep that engine running at low power for another 40 minutes. 40 agonizing minutes of limping through hostile airspace with a mortally wounded engine. That bomber and its 10-man crew made it back to England. A tiny metal ring delivered 10 men from the sky. But this breakthrough had its own costs. By 1943, Hastings was the single largest consumer of chrome in the entire United States, second only to the government itself. They received priority allocation for every shipment that made it across the Atlantic. This meant other domestic industries were forced to go without. The gleaming decorative chrome on cars, tools, and kitchen appliances vanished. The home front had to make do. New washing machines had steel components that rusted. Cars were painted in drab matte colors because chrome for bumpers and trim was unavailable. Then there was the ever-present issue of quality control. When you are plating 500,000 rings every month, errors are inevitable. A poorly mixed batch of plating solution, a sudden power fluctuation, a contaminated rinse tank, any of these could result in rings with a weak chrome bond. The rings would look perfect and pass a visual inspection, but under the stress of combat, they would fail. And when a ring failed at 20,000 feet, people died. Hastings established a merciless testing regimen. A sample from every single batch was subjected to a torture test. They installed the rings in a dedicated engine and ran it at maximum power and temperature for 24 hours straight. If a single ring showed any premature wear, the entire batch, thousands of rings worth tens of thousands of dollars, was immediately scrapped. There was simply no margin for error. A faulty ring wasn't a warranty issue, it was a potential death warrant. These test engines ran in soundproofed cells deep in the factory's basement. They roared day and night, the noise deafening even through the thick concrete walls. The vibrations were so intense they shook the entire building, causing tools to rattle on workbenches on the floor above. The engines were incredibly thirsty, consuming 20 gallons of fuel per hour. The factory maintained its own massive fuel depot, refilled daily by tanker trucks. The mechanics who operated these test cells were a unique group. They had to be able to diagnose an engine's health by sound alone. A subtle change in pitch could signal a failing bearing. A rhythmic knocking might indicate a slapping piston. A faint hissing noise meant a ring was leaking. They learned to identify dozens of failure modes just by listening, often hearing problems long before the instruments could detect them. When a test engine failed, the mechanics had to tear it down right away while it was still hot and smoking. They wore asbestos gloves and leather aprons, pulling off cylinder heads while the metal was still too hot to touch. They carefully extracted the pistons, measured the ring wear with micrometers, and documented everything with photos and detailed notes. Every single failure was meticulously analyzed. The data was then relayed to Fletcher and his engineering team, who used it to continuously refine the plating process. German engineers were aware of chrome-plated rings and had access to similar technology, but Germany was grappling with a different, more severe problem. They lacked sufficient chromium. Their supply lines were being relentlessly bombed, and their mines were being depleted. They experimented with alternatives like tungsten and molybdenum coatings. Some of these provided marginal improvements, but none could match the sheer durability of chrome. By 1944, German aircraft engines were failing at double the rate of American counterparts, not due to inferior design, but because of inferior materials. The Japanese military faced an even more desperate shortage. They had no domestic chrome sources at all. They attempted to import it from occupied territories, but American submarines were sinking their transport ships faster than they could be built. Japanese engineers had to resort to extreme measures. They would chrome plate cannon barrels, only to later strip the chrome off to reuse it for piston rings. They developed chemical processes to reclaim tiny amounts of chrome from used plating solutions. They would scrape chrome from damaged parts to be replated. It was never enough. By 1945, a Japanese aircraft engine was considered fortunate if it lasted 50 hours before requiring a complete rebuild. In contrast, American engines were consistently reaching 300 hours between overhauls. Some pushed 500 hours. A few legendary engines even surpassed 1,000 hours of service. That's the equivalent of flying from New York to Tokyo 25 times. These chrome rings were a critical, unsung advantage that contributed to American air superiority. They weren't the only advantage or even the most decisive one, but without them, the war in the air would have been longer, costlier, and its outcome far less certain. After the war concluded, chrome-plated rings quickly became the new industry standard. Hastings licensed its proprietary technology to its former competitor.
The number of maintenance hours required per flight hour plummeted by 60%. Engine-related aircraft crashes dropped by a staggering 75%. Those aren't merely numbers on a page. They represent lives.
thousands, perhaps tens of thousands of lives saved. There is a B-17 bomber on display that flew 35 combat missions over Germany. It suffered flak damage on 11 separate occasions. 3 of its 4 engines were replaced during its tour of duty. But when the plane was finally retired and its engines were torn down for a final inspection, the piston rings in its number 4 engine were still within tolerance, still sealing, still functioning perfectly. They had accumulated over 400 hours of flight time. They were Hastings chrome-plated rings installed in March of 1943. The engine that carried that plane through the war is long gone, likely melted down for scrap metal. But the rings themselves, those small, unassuming hoops of steel and chrome, are kept in a drawer in a Smithsonian storage facility. A curator once explained that they are preserved because they represent something fundamental. It's not just about the technology, it's about the mindset, the belief that when you are confronted with a seemingly impossible challenge, you do not surrender, you refuse to accept limitations, you find a new path. You innovate, you persist, and you refuse to stop until you find the solution. Howard Fletcher passed away in 1968. His obituary noted his 3-decade career at Hastings Manufacturing. It made no mention of chrome rings, the war effort, or his crucial innovation. It stated he was survived by his wife, 3 children, and 7 grandchildren. It said he was an avid fisherman. But somewhere in a forgotten filing cabinet in Hastings, Michigan, inside a dusty logbook from 1940, there's an entry on page 73 in Fletcher's own hand. It's a single sentence. November 14th, test successful. Chrome holds at 300 hours. No cracking, no wear. This will work. 4 simple words. This will work. It's a statement of profound American confidence. Not "this might work" or "this could possibly work." It's the conviction that if you apply enough intellect, enough sweat, and enough sheer determination to a problem, you will conquer it. That unwavering confidence built chrome-plated rings. Those rings kept engines running. Those engines kept planes in the sky. And those planes helped win the war. If you found this story of unsung innovation incredible, please hit the like button and make sure you're subscribed to WWII Record Hub. Today, piston rings are still coated in chrome. The modern process is more advanced, using different chrome alloys for even harder and smoother surfaces, but the core principle remains identical. A steel ring with a chrome-plated face will outlast any other design. And it all began in a small Michigan factory in 1940 when an engineer named Howard Fletcher looked at a failing cast iron ring and simply said, "We can do better." Every time you get in your car, chrome-plated rings are working inside your engine. You can't see them or think about them, but they are there, spinning thousands of times a minute, sealing, scraping, and managing heat, keeping your engine alive. They are the direct descendants of the rings that kept bombers flying over Europe. They are descendants of the rings that kept fighters airborne over the Pacific. They are descendants of the rings that helped secure an Allied victory in World War II. That is the nature of great engineering. The elegant solutions become invisible. They simply work, and no one is aware of their existence unless they stop working. Chrome-plated piston rings didn't stop. That's why few people remember them. It's why Howard Fletcher's name isn't found in history books alongside the generals and politicians. But it should be, because without him and his chrome rings, the war would have unfolded differently. It would have been longer, bloodier, and its outcome less certain. The next time you see an airplane trace a line across the sky, take a moment to think about this. Deep inside its powerful engines, tiny rings are spinning, sealing, and enduring. And they work because over 75 years ago, a man in Michigan figured out how to bond chrome to steel. He solved a problem that had stumped everyone else. He did it under immense pressure, with scarce resources, all while U-boats were trying to sink the very ships bringing him his materials. And he did it with the full knowledge that failure meant people would die. He did not fail. The rings worked, the engines ran, the planes flew, the war was won. And today, we don't remember his name, but we ought to, because engineering matters, materials matter, the invisible components matter, the people who solve impossible problems matter, and those tiny circles of steel and chrome, they mattered more than almost anyone can imagine. Hastings Manufacturing is still in business. They continue to make piston rings, and they still use chrome plating.
The very building where Howard Fletcher worked still stands. There's no statue, no memorial plaque. It's just a factory, making parts and solving problems, the same way it always has done. That's the engineer's legacy. They take on impossible challenges and make them possible. They take materials that shouldn't work together and force them to cooperate. They find the limits and then they shatter them, not for glory or for recognition, but simply because the problem is there and it needs to be solved. And if nobody remembers their names, that is perfectly fine. The rings remember, and the rings are still working.